Given the geometric series of the form 1 over 1 minus x, or in the summation of x to the power k from 0 to infinity, and also in expanded form as 1 plus x squared and so forth, for the absolute value of the x less than 1, find power series and interval of convergence for the following function. For the for part A, the f of x equals 1 over 1 minus 2x. We're going to use the pattern from the given series as 1 over 1 minus x is summation of x to the power k equals x to the power 0 plus x to the first plus x to the second and so forth. Therefore, for the 1 over 1 minus 2x, we can replace x with the 2x. So the series or the power series will become like 1 over 1 minus 2x as the summation of the quantity 2x to the power k from 0 to infinity. And next we're going to find the interval of convergence. To find the interval convergence, we have to know the r, which is the radius of convergence. Since the summation has the power k involved, we're going to use the root test as the condition for the series to converge. So by the root test, the series converges if rho, which is the limit as k approaches infinity of the k root absolute value of the ak less than 1. For this series, the ak is 2x to the power k. Therefore, the limit as k approaches infinity, the k root of the absolute value of the 2x raised to the power k must be less than 1. The power k and the k root take care of each other. So then we have the absolute value of the 2x less than 1, or absolute value of the x is less than 1 half. Then we have the interval that the series converges within, or we can say the series converges within the interval x greater than negative 1 half, less than 1 half. And then we're going to check the two endpoints at the left end, or at x equals negative 1 half. We have the series in the form of the summation k from 0 to infinity 2 multiplied by negative 1 half the quantity power k, or the summation of negative 1 to the power k from 0 to infinity. This series diverges by the divergence test, and also we're gonna check at the other end, or at x equals 1 half. Then the series becomes the summation k from 0 to infinity 2 multiplied by 1 half to the power k, or the summation of the 1 to the power k from 0 to infinity. This series also diverges by the same divergence test, because the limit is not 0, or the limit of the ak is not 0 as k approaches infinity. So we can say the interval of convergence is negative 1 half less than x less than 1 half, or negative 1 half open one half open. Part B, we have f of x equals 2x to the third divided by 1 minus x. By using the given series from the function 1 over 1 minus x as the power series summation x to the power k from 0 to infinity, or in the expanded form as 1 plus x to the second plus and so forth. And this series converges for the absolute value of x less than 1. We're going to write the function 2x to the third over 1 minus x as 2x to the third multiplied by 1 over 1 minus x to find the power series form of this. Then we can see that this is the same as 2x to the third multiplied by the summation x to the power k from 0 to infinity. And this becomes the series of the 2 times x to the third times x to the k from 0 to infinity, which is the same as the series or the summation k from 0 to infinity 2 multiplied by x to the power k plus 3. Next, we're going to find the interval of convergence. By finding the radius of convergence. To find the radius of convergence, we're going to use the condition of the ratio test. So by the ratio test, the series converges if the r equals the limit of the absolute value of the ak plus 1 divided by ak, k approaches infinity less than 1. The ak term for this series is 2 times k times x to the power k plus 3. So then the ak plus 1 is 2 times x to the power k plus 4. Then the limit as k approaches infinity, absolute value 2 times x to the k plus 4 divided by 2 times x to the k plus 3 must be less than 1 for this series to converge. Simplify the expression in the absolute value, we get the absolute value of the x less than 1. This one means the radius of convergence r equals 1. Or we can say the series converges in the interval x negative 1, x greater than negative 1, less than positive 1. And then we're going to check the two endpoints. At x equals 1 and x equals negative 1. So at x equals 1, the series, which is the series of the summation of 2 to multiply by x to the power k plus 3, k from 0 to infinity, replace x with the 1. Now it becomes the summation of 2 for k equals 0 to infinity. And this is the term ak equals 2. Take the limit of the ak. For k approaches infinity, we get 2, which is not equal to 0. Therefore, the series diverges at x equals 1 by the divergent test. And next, we're going to check the other end, which is at x equals negative 1. So the series becomes the summation k from 0 to infinity of 2 multiplied by negative 1 to the power k plus 3, which is the same as the summation of 2 times negative 1 to the power k times negative 1 to the power 3, which is negative 1, k from 0 to infinity, it's still in the form of the summation of 2 times negative 1 to the power k plus 1, which is the alternating series. With the conditions of the alternating series, number 1, the terms ak plus 1 less than or equal to the term ak, which is still true because the ak is 2 for the alternating series. But number 2, would the limit of the ak, which is 2, equal 0? The answer is no, it's not 0. So it doesn't satisfy the second condition of the alternating series test. Therefore, we're going to go back to use the divergent test. And by the divergent test, check the limit of the ak, which is 2 times negative 1 to the k plus 1 for k approaches infinity. It doesn't exist. It doesn't exist, it means it's not equal to 0. Therefore, we can summarize it as the series diverges at x equals negative 1 as well. So then at two endpoints, the series does not converge. So we can say the interval of convergence is the interval negative 1, comma 1.